So now I've got a graph of force versus stretch distance. So the relationship that is going to be involved here is going to be Hooke's law. But this question asks you to plot data points. And you've just got to be really careful to make sure you put them on the correct axis. In this particular case, they already gave you the label for the variable and for the unit. Sometimes you need to do that. So for example, you'll look at 0.37, 0.98. So notice the spacing. Each one of these is 0.02. So 0.37 for the length and 0.98 for there. I'm going to pause it here while I plot the other ones because it's probably boring to watch me do that. So now that those are plotted, what we need to do is we need to draw a line of best fit. So you're going to draw the line that seems to best go through the data points. Now it may not necessarily touch all of them. In fact, it probably won't. Just do your best to get sort of an average. So about like that maybe. Now the third question they ask is to determine the length of the spring before any weight was attached. Another way of saying that is when was the force 0, where was the spring? Because remember, the Hooke's law equation, the x there is actually the distance from the rests. So if this is the normal length of a spring and you hang masses on it, it's going to get longer and longer, and it's that difference in distance that's the x. So right here, this point right here where it intersects is going to tell us when the force is 0 newtons, what was the value of x. In other words, what was the rest length of the spring. And in this case, you can see it's about 0.29 meters. The other question on this page is one about centripetal force, but it uses very large numbers because we're talking about the Earth going around the sun. They tell us that the Earth travels at a speed, tangential velocity, of 3 times 10 to the 4 meters per second. So the equation we're going to use is centripetal force equals mv squared divided by r. We're going to have to look up the mass of the Earth, and we're going to have to look up the distance from the Earth to the sun. So to do that, we're going to look in our reference table. It's on the front page. When you look, you can see the mass of the Earth, 5.98 times 10 to the 24 kilograms. And the distance to the sun is this mean Earth to sun distance, 1.5 times 10 to the 11 meters. So you've got to be careful and you've got to look those up. But plugging this information in, mass of the Earth, 5.98 times 10 to the 24th kilograms. The velocity is 4 times 10 to the 4 meters per second, and that's squared. And then the distance, the mean Earth-Sun distance from the reference table is 1.5 times 10 to the 11 meters. Now, you've got to be careful when you plug this in your calculator, especially if you're not using a TI-84, TI-83, or something you're comfortable with plugging in scientific notation. So while you can plug it in that way, let me show you a way that you can do this with even a 4-function calculator if you want. Take the powers of 10 and the regular number part, if you will, separately. So this is 5.98 times 4. Now 4 squared is going to give you, sorry, it's supposed to be 3. That's my mistake. 3 squared is going to give you 9. And then 1.5 on the bottom, like this, times 10 to some power. Now, remember, when you have powers of 10 and you multiply them, you add the powers. So 10 to the 4th squared is 4 plus 4. That gives you 8. So you have 24 plus 4 plus 4 because of the squared. And then when you divide by a power 10, you subtract. So that's minus 11. What does this all mean? When you plug this in, these numbers, you get 35.8. And 24 plus 4 plus 4, 32, minus 11, that's going to give you 10 to the 21. So the answer would be 35.8 times 10 to the 21, and the unit would be force. Or, of course, in true scientific notation, you could do 3.58 times 10 to the 22 newtons, which, of course, is a very large number because you're talking about the force of the sun on the Earth.